I mean, I would find it fun, but that's kind of why I'm here. All right, so now we kind of go back to scratch because we have to discover all the other types of trig functions using the limit definition. But now we have an idea that if I could just get the parent function, that I can tweak the derivative of the parent function based on whatever the coefficient is inside the expression. Right? So if this were secant 2x or secant 5x, it's going to be easier to handle. Now, that's not to say that it's always going to work out when you have something other than x in there, because if I have something like the secant of the natural log of x or something like that, composite functions, then all bets are off. That's a different story altogether. But for now, we do seem to have a rule that we can apply, at least in some situations. All right. Now, this one's a little bit more interesting because you got a few different approaches that you might consider taking. First thing I would recommend is a very subtle maneuver. Make the secant into 1 over cosine. All right. We're going to apply the limit definition again. It's still going to be one of those cases where we're best served by using the traditional one. So limit as h approaches 0 of 1 over cosine x plus h minus 1 over cosine x all over h. So it's definitely going to be more challenging right off the bat because I have to get a common denominator before I can even get started with my trig properties. All right, so let me do that. So top and bottom of this one by cosine x. Top and bottom of this one by cosine x plus h.
Why is it not just cosine?
Why is it? Say it again.
Never mind.
You good? All right, so I'm going to go a little bit smaller. Limit as h approaches 0. Now my numerator is just going to be cosine x minus cosine x plus h. The denominator is going to be a little funkier, but not too crazy. So cosine x minus cosine x plus h over cosine x times cosine x plus h. Now we have that h on the bottom that could be thought of as h over 1. If I keep change flip that, it's going to put it into this denominator as just an h. So save yourself a step and just chuck it in there immediately. All right. So at this point, you're kind of ready to get started on the expansion, going down this road to try to see if you can expand it for the purposes of cleaning it up, right? The only way it's going to happen, there are a couple of different ways it could happen, but the most useful approach would be to swap out the cosine x plus h for its equivalent identity. So this guy has to go. So limit h approaches 0, cosine of x minus parentheses, just to play it safe, cosine x, cosine h, minus sine x, sine h. All over the stuff on the bottom.
Are we gonna have to have all those trig rules memorized? Like cosine of x plus h?
more or less anyway. Because the not the short. What word am I looking for? The bailout is to store it into your calculator in a program. So, but you don't want to have to do that for every single possible formula that you could possibly do that that you could be expected to know. So, hopefully you know something.
But you said that's okay if we do that?
Yeah. That's why I went over it that one day just to show you how you can do it so that you don't get error messages all the time, So anyway, so I can distribute the negative. You could do it on the fly if you want. Just change signs here so that you don't have to rewrite the next step just for the purpose of changing a sign. Probably a good idea.
Sorry, it was bugged.
B?
Yeah, I just don't do bugs. I don't do bugs. I'm sorry.
I respect that. So I earned like a massive amount of street credit at my kid's elementary school because a bee stung me and I didn't react. What the kids didn't know is that I have like numbness down my extremities because of my spinal condition. So I didn't feel it. So all they saw was me get stung, not even react, just kind of look. The bee, like the stinger falls off and it dies, right? So the kids like go running away screaming at the top of their lungs. They're like, Mr. Cat is so tough. The bee stung him and died. And, he killed the bee just by it was great. I didn't feel it, so it was a win-win for everyone except for the bee. The bee's dead. So I'm, for some reason, going crazy with parentheses. I don't know why. I couldn't stop myself. Yeah, it just is what it is, I guess, as Mr. McCallie would say. Or as Mr. Shippey would say, yep. Or, hey man. That's a good Shippey.
Hey, can I borrow some textbooks? It's like,
So he's like the epitome of chill.
Library duty because kids could literally be like yelling at each other across, and he just is like reading his newspaper.
Yeah, which is the opposite of me in library duty, which many of you have experienced. I'm like, I'm just trying to grade these papers. Can you just stop? Just stop, yeah, please. I only start losing my mind in there when I've had to reread the same problem like 14 times because of the distractions. That's just a me thing, I guess, but I guess I complained enough, so now I got freshman study hall, which is like infinitely worse. They're like, oh, you don't like library duty, huh? Oh, okay. Like, thanks a lot. I think the freshman study hall issue revolves around the fact that they don't understand how to play the long game. Like, I'm going to be here for a long time. I've been here for a long time. I'm going to be here for a long time. And so it doesn't occur to them that our paths are going to cross again at some point. So when they're being like not the nicest people in the world to me, it does not occur to them that like 3 or 4 years later, they could be sitting where you're sitting. Like with me as a teacher, they will have forgotten that moment. I will not have. So, that's how it is. So we get to this step here, and it's a god-awful mess. I'm sorry, I can't see God in the classroom. But believe it or not, it's pretty much done. The problem is solved. It just looks like a terrible disaster, but it's a beautifully terrible disaster. Because tucked in there is this, right? Okay, you're not impressed. Got it. Yeah, I'll accept that. Yeah, a nice whoa. Something of that ilk.
Oh, and then the sine H and the H.
There it is.
Wow.
Oh, wow. I'll take a wow, too. I like wows. So those will cancel out also. All right. Now, you might have canceled out the cosines here, too. That's a good move, but ultimately irrelevant, because this is going to 0, so everything here is going away. So canceling out the cosines is like a good observation, but it doesn't really do anything. What we do have here on this one is the sine of x over the cosine x times cosine x plus h. All part of the limit as h approaches 0. All right, so I almost fell. I haven't fallen yet. It really is really just a matter of time. I'm due to go down at some point. And it's not like dropping a feather. It should be like a ton of bricks. And so, I don't know, it's not going to be pretty. So anyway, when I replace the h with a 0, I get 2 cosines on the bottom multiplied by each other. So I could actually multiply them by each other, but I'm actually not going to. I'm just going to leave it, at least for the moment, as cosine times cosine. You might be tempted to write it as cosine squared, but a simpler form would look like this. I can take the sine over cosine and make that into what? Tangent. I can take the cosine that's on the bottom here and make that what? Secant. All right. And this actually is the derivative, or the more popular way of writing the derivative. It's just for some reason they like to put the secant first. So we say secant times tangent. So that would be the derivative with respect to x of my secant function. So that's a pretty significant departure from, look at that mess, it's great. I fit it perfectly. Yeah, it's a significant departure from what we had, because sine was cosine, cosine was negative sine. Secant is somehow secant tangent. It's kind of like defining the word, using the word in its own definition.
So like in the brackets, there's like still an H, and then when we drop down, there's like not an H anymore. Where does it go? Oh, we apply the limit. Okay.
Exactly.
If on a test you wrote tangent x times secant x, would you get cosine?
Not at all. Yeah, perfectly fine. And in fact, on a test, if you wrote it as sine over cosine squared, that's fine too. I just wanted us to get to what every textbook calls the derivative of secant, whether we like it or not, you know. So we have other problems here, like tangent, cotangent, and cosecant. Now, we learned something yesterday that allows us to get the answer for the derivative of cosecant immediately without doing any of this. All right. So let's go back what I have on the board. So we know that the derivative of sine is cosine, and we know that the derivative of cosine is negative sine. All right. So the relationship between these two is what? What are they? Relative to one another? There's a special word for it. Having to do with that.
Complement.
That's the root of it. Yeah, they're complements of one another. We call those cofunctions. All right, but the co stands for complement, so you're right. That's actually a better answer than I was looking for, so it's really good. Yeah, because complementary angles are angles that add up to 90 degrees, right? But in the context of the graph, they represent 90-degree translations, so horizontal movements. If you shift a sine wave 90 degrees, you get a cosine wave. If you shift a cosine wave 90 degrees, you get a sine wave. So that's why they're complements and therefore cofunctions. All right? So these are cofunctions of one another. What's the relationship between these two? Well, the derivatives themselves are, the co part is still going to apply. They're cofunctions directly, or was some kind of an adjustment made? Oh, because this was a positive sine to a positive cosine, right? And with the signs were inverted, so we would say negative or opposite, negative cofunctions. All right, so if I know, for example, that the derivative of secant is equal to secant times tangent, I can figure out the derivative of its cofunction, cosecant, by applying that relationship. So first, it was positive, so make it negative, and find the cofunctions of each of these. I love when people pack up right at the moment where I give you a piece of information that would make your life easier. It's cool, you don't have to write it down or anything. You don't have to get it right on the test. So tomorrow we'll have plenty of opportunities to practice with this because you do need time, definitely time to play around with this stuff. All right, so number 7 on the next page. It's obvious that the type, or let's see if I can say this the right way. The difficulty level is directly related to the type of function that you're working on. Yeah, I think I said it the right way. So we're talking about like, if I'm dealing with a power function, so something like x to the 4th power, that's not going to be hard to work with. But if I deal with a radical function, that could be a nightmare. You know, trig functions are definitely a little bit more involved. So we're journeying beyond the world of sines and cosines, so this is going to get a little bit more intense. All right, but not devastatingly so, I don't think. That being said, all trig functions could be represented in terms of sines and cosines, so go with what you know. Tangent is equal to sine over cosine, so let's make use of that fact. There is a way to do it just working with the tangent function and applying the limit definition to that, but it's not fun. Cotangent is the cofunction. So once we figure out tangent, we'll know cotangent. But we have to do it first, yeah. So limit as h approaches 0 of the sine of x plus h over the cosine of x plus h minus the sine of x over the cosine of x all over h. In for a ride now.
Is it okay to use h if like it's h of x?
Yeah. It's a good point though, I should probably change that. Just for clarity. Try to stay away from that sort of thing, but it's all right. Okay, so it looks like we need to do some common denominatoring, which is exactly what you wanted to do. Now you woke up this morning and you're like, you know what, I'm really dying to add and subtract fractions, but I don't want to just do it with any fractions. I want some like monstrous looking fractions. And yeah, guess what? Here we are. So we're gonna put this all together, and then I'll perform some black magic, and then we'll have the answer. It'll be great, I promise. All right, so I'm gonna rewrite the there's no like terms to combine or anything. I just gotta go with it. But each term or each component has a sine and a cosine. So this is actually shaping up an awful lot like the expanded form of the sum identity for sine, or a difference identity. So I'm going to write it as sine of x plus h cosine of x minus cosine x plus h sine of x. All right, that's all over my common denominator of cosine x cosine x plus h. And that whole thing is over h, which is over a 1. If you keep change flip it, that puts the h into the bottom of this fraction, just to save yourself a step. You know, because you would just basically be taking that, keep changing and flipping it, and writing a whole new line, writing the whole thing over again just to put an h in there. That doesn't seem to make sense. So then you get to this step, and if you're not at least familiar with the sum and difference identities, then you're at a loss, because then you try to start canceling things out. Maybe you even look for a property like a limit rule, but really this is actually way easier. So let me show you. So sine of a minus b is equal to sine of a cosine of b minus cosine a sine of b. All right. So it's like, okay, that's wonderful. How is that helpful? Well, if the a is equal to x plus h and the b is equal to the x, then what I would have here, just doing simple substitution, not sim, sine, x plus h minus the x equals the sine of x plus h cosine x minus cosine x plus h sine of x. All right, so by using this rule and substituting in these values, I get this expansion. The right-hand side of which is exactly the same as the numerator in my limit. The left-hand side actually simplifies down, shockingly, to just a sine of h. So what that's telling me is that I can swap out this entire expression for this. So I have sine of h on top.
Wait, so when you do keep change flip, you cross multiply, that's how you have the h in the bottom?
I multiplied across. So I took the h over 1 and multiplied it by the top fraction.
Oh, it flips
One,
in the
yeah.
Wait, I'm confused. How did the sine of h happen?
x minus x is 0.
That would do it.
Every time. So now I have a sine h over h as a factor of this fraction. Sine of h over h goes to a 1, yeah. So limit as h approaches 0 of 1 over cosine x plus h. Apply the limit, you get 1 over cosine x times another cosine x, right? Because if I replace the h with a 0, x plus 0 is x, which is the same as 1 over cosine squared, which is also the same as what?
Sine squared. Or sine squared x.
Not sine, secant. So the derivative of tangent, by definition from here on out, but we just discovered it, is equal to secant squared. All right.
Can I write f1 like of x? Is that the same as d over dx?
F prime of x, yeah. Other way. Other way is fine. So that negative cofunction relationship is kind of a nice little bailout, because in this case we found the derivative of tangent. You're probably not overly eager to start the process all over again to find the derivative of cotangent, only to find out that you could have gotten it just by knowing this fact. So if two functions are cofunctions of one another, and all that means, again, folks, it's not that complicated. One has a co, the other doesn't. All right, tangent, cotangent, sine, cosine. All right, that's what makes them cofunctions. The co stands for complement. That's not even really important right now. All right, if they're cofunctions, then their derivatives will be negative cofunctions. So tangent has a derivative of secant squared x. So the derivative of cotangent would have to be negative, or the negation of that. If it was already negative, I would drop the negative. But there was none, so I'm introducing it. So I just want to create the cofunction of this. Cosecant. So without doing any of that work, we now know that the derivative of cotangent is negative cosecant squared. I did all the work for number 6 to get secant tangent, so we know the derivative of cosecant. But tomorrow we're going to spend some time, or you're going to spend some time working through these just to get your hands dirty a little bit.
So are you going to ask us on